Math over here, and this is the 2013 AIME 1 Problem 10. Here's a view of this problem. There are non-zero integers a, b, r, and s such that the complex numbers r plus si is a root of the polynomial this. For each possible combination of a and p, let pab be the sum of the zeros of p of x. Find the sum of the pab's for all combinations of a and b. Okay, so first let's just copy p of x over here. Okay, and then we know that the roots are r plus si, and then by complex conjugate theorem, r minus si must be a root. And then now, since this is a polynomial of degree 3, it'll have 3 roots, and we know it's not irrational or complex, meaning it must be rational, and it's called the rational root q. So therefore, the p of x can be expressed as x minus r plus si times x minus r minus si times x minus q. Okay, let's just expand this and maybe match coefficients with the original polynomial. Expanding this out will give us x squared, and then this is negative x. Factoring out the negative x will give us 2r, so negative 2rx. And then this will give us r squared minus s squared. R squared plus s squared. And this is times x minus q. Just make sure x, yep. And then let's multiply this out to get x cubed minus 2rx squared, what? Minus 2rx squared plus rx times r squared plus s squared, minus qx squared plus 2rqx minus q times r squared plus s squared. That's great. Now let's maybe combine like terms. We have the x cubed coefficient by itself. Combining like terms gives us plus x squared times negative 2r minus q. Okay, and then combining like x terms gives us x r squared plus 2rq plus s squared, and then minus q times r squared plus s squared. And then this is equal to our original polynomial, which is x cubed minus ax squared plus bx minus 65. Alright, now coefficient matching, we get that negative 2r minus q is equal to negative a. Therefore, a is equal to 2r plus q. B is equal to r squared plus 2rq plus s squared. And then negative 65 is equal to the negative of this, so 65 is equal to q times r squared plus s squared. Now it's actually pretty clear. Okay, so now let's see what the problem's asking for again. For each possible combination of a and b, for each legal a and b, let p of a b be the sum of the zeros of p of x. So p a b be the sum of the zeros. The sum of the zeros by Vieta is just a. So we just need to find sum over the values of a's. Okay, I think I can handle that. So 65 is equal to q times r squared plus s squared. Let's look at the third condition, because the third condition is the only one with the constant term. Therefore, we can actually get the most information. And then I'm gonna do this as follows. I'm gonna consider what r squared plus s squared is in terms of q. If q say is 1, r squared plus s squared is equal to 65. And then now we can extrapolate values for r and s. For example, when in general, when dealing with this, you always want to like look at the highest number. Highest number we can have is 8, and then the other one will have to be plus or minus 1. And of course we can reverse the order, and putting plus or minus for anything is legal because when we square it we'll just get a positive. Okay, and then let's go down one. 7, for 7 we'll get 7 and 49 and 16, so that's 7 and 2. Again, plus or minus 7, plus or minus 2, and then plus or minus 2, plus or minus 7. And then over here I'll just put this as for q is equal to 1. Okay, how about r squared plus s squared? And then the 65 is rather convenient because 65's prime factorization is 13 times 5. They'll have 2 times 2, 4 factors. So there's only a limited cases of r squared plus s squared. So r squared plus s squared could be 13. And in that case, we can take r equals 3 and then s is equal to 2. Of course, they can be plus or minus. And of course, they can be reversed. And then what else can we do? We can take, well, if we take r is equal to 2, then this case just occurs, so that's about it. And then I should actually add for this one, we can take 6, and we can take 5, and then we can take 4. None of the rest will work. So now let's go to r squared plus s squared is equal to 5. And if that's the case, there are only select few, right? R can be 2, s can be 1. So plus or minus 2, plus or minus 1. And then we, of course, reverse this, plus or minus 1, plus or minus 2. And then r squared plus s squared could be equal to 1. And in that case, we have plus or minus 1. Sure, plus or minus 1, plus or minus 0, plus or minus 0, plus or minus 1. So for each choice of r and s, r plus si is a root and r minus si is a root. Therefore, this plus or minus in the s is actually kind of redundant because for every choice of r plus si, we're automatically going to take an r minus si. So therefore, we can disregard the plus or minus sign and now focus on summing throughout the a's. So now we focus on this condition to sum for the a's. Well, for this is when q is equal to 1, right? So this is when a is equal to 2r plus 1. Now this one's the s's stay stagnant, right? And then we're summing this stuff, plugging in 8, plugging in negative 8, plugging in 1, plugging in negative 1, and so on. That'll cancel except we're adding 1. Each of the times that'll be 2, 4, 6, 8 times. So we're adding 8 ones. Next, what happens when I'll add, this is when q is equal to 5. This is when q is equal to 13. And then this is when q is equal to 65. So 8 to our running count. Okay, when q is equal to 5, we have 2r plus 5. Again, the stuff cancels, right? We have 4 of these. The r's just cancel. We're just adding 4, 5, so 20. And then finally, and then for this one, you'll see why I said finally later. And then for this is a is equal to 2r plus 13. Okay, same deal here. We're doing it 4 times, 52. And then once we get to 65, that's a is equal to 2r plus 65. But then these terms just negate themselves, so we get a running count of 0. So our answer is therefore 8 plus 20 plus 52, which is 80. And we are done.